Hi everyone, welcome to this episode of KuTube. Today we're going to be exploring standard form of a quadratic function. Before we begin, please make sure you have the following materials out. You're either going to want a printed copy of the notes, or if that's not available to you, make sure you have some graph paper because we will be graphing today. Alright, so let's begin. Today we're going to be exploring the first form of a quadratic function, which is standard form. We've done some previous work with exploring some of the components of a quadratic function and how does that transform our parent function. But today's goal is really special. We're going to identify what each value of standard form does to the quadratic function. We're also going to apply what we know about quadratic functions to solve real-world application problems. All right, so let's begin. Remember, a quadratic function is a function that has the highest degree of 2. In standard form, it's y equals ax squared plus bx plus c, where a, b, and c are all real numbers, and a is not equal to 0. Now, as you can recall, we talked about how a can't be 0 because if a is 0, that first term will kind of cancel out, and now I'm left with a linear function, okay? So we definitely need a real number for a. Below, you're going to see some examples listed, all right? As you can see, every single one of these examples has a highest degree of 2. But when we take a look at the last two examples here, there's some special features I want to just make sure that we're really comfortable with. Sometimes you might get a quadratic function that's not written in standard form, and that's okay. All right, but when it's not written in standard form, you're going to just want to make sure, take the time to rewrite it. Another thing you might notice is that sometimes we might not use x and y, and that's all right too. All right, so making sure that we're comfortable with sometimes our input value might be a different variable, and sometimes our output value might be a different variable. I just realized there's a little bit of a typo here, so I apologize. Please write function properly in your notes. All right. So we've done a lot of work with identifying some components or some features of quadratic functions. You have 4 examples here. The first 2 examples ask you to identify the vertex given a graph. In example C and D, I'm asking you for some requested material just given a function. All right, so go ahead and pause the video and just quickly answer A, B, C, and D. And when you're ready, you can unpause the video. All right, so hopefully you guys have answered A through D. Like TV magic, let's look at each of the answers. For A, you should have noticed that the vertex is 4, 3. Remember that vertex is that highest or lowest point or that turning point of your quadratic function. Please make sure that you have parentheses around your ordered pair. All right, and this is a max. For example, B, same idea. My vertex here is the lowest point of my graph, so it's -3, -3, and it is a min. For C, the direction of the opening is down. We know that because in this case we've got a negative a value. If you need to draw this really quickly to then identify that we have a max for our vertex, that's totally fine, okay? Really just showing whether or not that quadratic function is facing up, that parabola is up or down. Now in this case, since we have a fraction that is less than 1 for my a value, we know that this is a wider parabola than my parent function. And another way of expressing that is by saying it's a vertical compression. All right. Now in example D, similar, we're going to take a look through it. The direction of the graph is facing down, which means it's a max. We know that this is narrower, and even though it is a fraction, this fraction is larger than 1, right? 5/4 is 1 1/4. All right, so this is called a vertical stretch, using some of that vocab. All right, so this is all a review from last time. So let's bring everything together. We know that standard form of a quadratic function is y equals ax squared plus bx plus c. We've already talked about how a affects the graph and how c affects the graph, all right? So those should be nice and easy. So let's review those really quickly. Let's start off with a. A affects the graph in a lot of ways, all right? And this is everything that's really talking about a here. When a is less than 0, we know that the parabola opens down, right? If the a is less than 0, that means that it's negative. So it's facing down. When a is greater than 0, that means that my parabola opens up. All right, if you need to, you can kind of also draw that. The other thing that a affects is the width of the graph. When the absolute value of a is less than 1, the parabola is wider than the parent function. When the absolute value of a is equal to 1, the parabola is good, the same width as the parent function. And when the absolute value a is greater than 1, the parabola is narrower, right, than the parent function, or stretch. Then we explored what does c do to our graph. All right, so we're going to look down here. Remember, when c is less than 1, the graph translates up. When c is when c is less than 0, the graph translates up. And when c is greater than 0, the graph translates down. So A affects the direction of the opening and the width of the graph. And C affects whether or not the parabola shifts up or down. Which then brings me to B. What does our B do? Now, as we kind of explored in class, right, B really just affects the axis of symmetry and our vertex. Okay, so B has a lot of features to it, and we're going to really explore a little bit of that in a moment. But let's take a look at the right-hand side of this table. Now, everything on the right are just some helpful hints here. So the first thing that I'm going to really talk about is how to solve for the axis of symmetry. Now, we know if we have a parabola, all right, we do have a line that goes down the center of my parabola, splitting it in half, and that is called our axis of symmetry. That's the vertical line that crosses the x-axis. The equation to find the axis of symmetry is x equals negative b over 2a. So that's a really important equation to know. Some other features I might ask you to solve for is the vertex. All right, well, we know that our vertex is always located at the highest or lowest point. So in this case, our vertex is here, and it always lies on my axis of symmetry. Since we know the vertex exists on the axis of symmetry, what we can simply do is plug in my axis of symmetry as my x value for my coordinate, all right, and then solve for y. So for instance, what this will look like is something like my x value will be negative b over 2a, and my y value will be the function of negative b over 2a. I apologize that this is a little messy. Some other things I might ask you guys to solve for is the x-intercept. If so, we also know those are called the roots, but simply we just plug in y for 0 and solve for x. To solve for my y-intercept, I simply plug in x for 0 and solve for y. Okay? So a lot of good features here. I would really recommend, if you have the notes printed, great, write this down. If you're just using a scrap paper, you might want to screenshot this and put this into like a Google Doc. All right, let's take a look at our first example. A common example I might ask students to do is to graph quadratic functions in standard form. Now, yes, of course, we can use a graphing calculator or Desmos, which would make this a lot easier, but there's a lot of value in being able to graph a quadratic function by hand. So let's take a look at this. We have f of x equals negative x squared plus 2x plus 3. So the first thing I'm going to do is to identify my a value, which is negative 1, my b value, which is positive 2, and my c value, which is 3. Now, when I want to graph it, I really want to start with my vertex. So to find the vertex, which is an ordered pair, right, I need to first find my x value. And to find the x value, we're going to use our axis of symmetry, which is negative b over 2a. So I'm going to plug in negative b, which is negative 2, over 2 times negative 1. We get negative 2 over negative 2, which gives me positive 1. Now that's just my x value. So now I need to go back and plug in and evaluate my function for f of 1 to get my output, or my y value. So I've got negative 1 squared. I don't need parentheses because that power of 2 only belongs to the x, plus 2 times 1, plus 3. So we have negative 1 plus 2, which is 1. 1 plus 3 is 4. All right, so now I have my vertex, and my vertex is 1, 4. Now that I have found my vertex, I'm going to zoom in a little bit just so hopefully this is a little bit clearer for us. We're going to create a table of values. All right. Sorry for the pause, I'm just trying to rearrange my pen here for a little bit. All right, so the first thing I'm going to do is to create a table, an input-output table. And for a quadratic function, I like to plot 5 points. The reason for that is if I only plot 3, it's not really going to give me a good idea of what that quadratic graph, that function looks like. It's not going to really show me if it's wider or narrower, right? So 5 points gives us a good idea. All right, we can plot the vertex, which I'm always going to put in the middle. 1, 4, I'm going to use a different color. All right, and I'm going to choose values below my x value of 1. So in this case, 0 and negative 1. And I'm going to choose values above that x value. So 2, 3. And then what I'm going to do is I'm going to plug in each of these x and y values into my original function to figure out what my y value is. So we have negative times negative 1 squared plus 2 times negative 1 plus 3. All right, as I'm doing this on my paper, you're going to want to do it on yours. All right, so we get our output of 0. So now I'm going to plug in 0, negative 0 squared. This is always nice and easy, right? 2 times 0 plus 3. 0 plus 0 is 0. 0 plus 3 is 3. All right, we already have our 4 done. Now I'm going to double check that when it reflects over that axis of symmetry, right, does it come out to be the same on the other side? So I'm going to input in 2. We've got negative 2 squared plus 2 times 2. Remember, you don't need that parentheses around that initial 2 because that x1 and 2 only belongs to the x. You get negative 4 plus 2. All right, plus 4 plus 3, that gives me 3. Then we're going to plug in 3, negative 3 squared plus 2 times 3 plus 3, so that's negative 9 plus 6 plus 3, that gives me 0. Now I'm going to take each of these ordered pairs, I'm going to plot them. Negative 1, 0, 0, 3, 1, 4. I start to notice that my graph is facing downwards, and I'm going to double check. And in fact should face downwards because my a value is negative. We see 2, 3. You see 3, 0. All right, and you're just going to try your best to draw this as best as you can. All right, now we're going to take a look to see if we can identify some of the requested information. Our vertex is 1, 4. Okay, oops, let me make that look more like a comma. The domain I'm scanning from left to right for my x values is all real. What's my range? Good, negative infinity all the way to 4 inclusive. We notice that in this case, we're dealing with a vertex that's a max. The direction of the opening is down. The axis of symmetry is that vertical line that goes through the x-axis. This is x equals 1. And we're going to compare this graph to its parent function. So I look here, and we notice that my value of a is negative 1. So in this case, how does this graph compare in width to the parent function? That's correct. It has the same width. All right, and that's all we're going to write here as the parent function. All right, so now we've talked about steps in order to graph a quadratic function using standard form, and we're really building on that idea of finding that vertex by using that equation x equals negative b over 2a. All right, so you have 2 examples here. I want you to pause the video, graph each of these functions, and then identify the requested information, and when you're ready, you're going to unpause the video and see if you got them correct. All right, so hopefully you finished number 1 and 2 like TV magic. Let's see if you got the correct answer. All right, got a lot of information here, so I'd recommend that you guys pause the video, double check, making sure that your graph looks like mine, double check all that requested information. All right, so finally, let's get to an application problem. We talked a lot about how a quadratic function looks, how do we identify a quadratic function, let's talk about how we apply it. So in this example, a ball is thrown into the air with an upward velocity of 40 feet per second. Its height h in feet after 10 seconds is given by the function h equals negative 16t squared plus 40t plus 6. Sometimes it helps us to really kind of draw a quick little visual. So if I kind of drew this as a graph, right, we know that this is kind of facing downwards and it's really not starting at 0. All right, so we've got something that kind of looks like this. Now in part A, it says in how many seconds does the ball reach its maximum height? Now if you'd like to try out A and B on your own, you're welcome to pause the video and try it out and then follow along with me to see if you got the correct answer. Otherwise, you can just keep listening. All right, in order to figure out how many seconds does the ball reach its height, the first thing I'm going to do is, well, I know my independent variable, my x, is time. And I know my y, my dependent value, is going to be the height. So sometimes it helps us to label it. Now I want to know how many seconds does the ball reach its maximum height. Well, the maximum height is right here, so I need to figure out what the time is. Now if I take a look at that dotted line that I just created, what are we technically solving for? Good, my axis of symmetry. So this is just a nice way of asking for the axis of symmetry. If we look back into our notes or kind of think back to what we discussed in the beginning class, right? The way to find the axis of symmetry is to use the formula x equals negative b over 2a. So I'm just going to simply plug in my value b, which is negative 40 over 2 times negative 16. I get negative 40 over negative 32, and that simplifies to 5 over 4. Okay? Now, my x value is 5/4. We're going to answer in the context of the problem. You never really hear someone say 5/4 of a second. So we're going to convert that, 1 1/4, or we can say 1.25 seconds. Now we know at 1 1/4 seconds, it's reaching its maximum height. What is the ball's maximum height? Well, now I need to know my y value, right? So we're going to take that 1.25 seconds, and we're now just going to evaluate our original function. We're really looking for that vertex, okay? The y value of my vertex. So I'm going to say h is equal to -16 times, I'm not going to use 1.25, I'm going to go back to my 5/4. I think it's a little easier to solve it that way. Plus 40 times 5/4 plus 6. I solve that out, all right? We get h equals 31, all right? So the maximum height, my stylus pen isn't great, is 31 feet. So in other words, if I looked at this point here, we have 1.25, comma, 31. All right, where that 1.25 represents my input, which is my time, the 31 represents my output, which is the height. All right, so hopefully you understood that. If you need to kind of pause the video, you just kind of finish solving it out. You can do so right now. My key's over here. Otherwise, let's reflect really quickly. We've talked a lot about some of this vocab the last few days. We've just introduced standard form. We have 2 other forms to talk about. To pause the video if you need to, take a look and test yourself. Do you know all this vocabulary? Otherwise, thank you guys for watching this episode of KooTube. Don't forget to like and subscribe. Bye, everyone.